The next thing we want to do in the course is to be able to talk about rotational motion a little bit more carefully. So, for example, say you just have some object like this, and we want to be able to describe the object rotating around. We've developed in the last section of the course a lot of the tools and terminology we need to even begin to describe this. Angular velocity, angular acceleration, things like that. But what we don't have yet is actual physics principles that tell us how an object is going to accelerate in response to forces when it comes to rotations, pure rotations, and also rotations that happen along with other kinds of motion. In order to do that, we need to develop a few more fundamental concepts. I think the first one we need is when we talk about rotations, we often want to say like, well, this object is rotating about an axis pointing through the object's center, because that's the center of the circle where the object is rotating. But then again, you could also rotate the object like this, in which case the center is over here. So we need some concept of what the center of an object really means. The way we describe that in the world of physics is with something called the object's center of mass. So the center of mass, it's basically the object's average location in the sense of kind of what we mean by the center of an object. It's not necessarily the geometrical center of an object. So not necessarily in the center of the object in terms of size, but it's the object's center in terms of its physics, basically. So let me give you an example. The quick kind of way to find the center of an object that basically works in everyday life type situations is like if you try to balance something on your finger, the point that it balances on there will be just below the object's center of mass. So like for this pen here, the object's center of mass is going to be right here. Now, I don't know if you can see, it's not quite exactly in the center of the object. The center of the object is probably about here, so it's a little bit off center. You can also have more extreme examples, like a hammer here, where if I try to find the center of mass of the hammer, you can see it's about here. In this case, nowhere near the actual geometrical center of the object. So what's going on here? Why isn't the center of mass of these objects in the center of the object? And what determines where that center of mass is actually located? So if the object is asymmetrical, so that more of its mass is concentrated on one side, its center of mass will be more towards the heavier side of the object. So like in the case of this hammer, most of the weight of the hammer is in the head. The handle's really not that heavy. So as a result, the handle doesn't contribute very much to the physics. The head contributes more to the physics. So where the center of the object then turns out to be is it's more weighted towards the head than it is towards the handle. So you have a center of mass way over here, just a little bit off of the head of the hammer. And like with the pen, in this case, the side with the cap is going to be a little bit heavier than the side without the cap because the cap adds some extra weight to this side. So that's going to slightly shift the center of mass off center. If you need to determine where the center of mass is located on an object, we are only going to learn how to do this for a system of small point masses. So we're not going to learn how to do this for something like the hammer or the pen, really, just because the math involved in that is a little bit difficult. But for a system of small point masses, so for example, let's say you have a system where you've got maybe an object here and you have maybe a heavier object over here. And maybe they're connected by like a very lightweight rod like that. And let's say maybe, for example, this guy has mass m and this guy has mass 2m. And let's say that there's L from the center of one to the center of the other one. We can expect conceptually that the center of the mass should be on the right side of this object. It should be closer to the 2m than it is to the m, because the 2m is going to be heavier. The 2m is going to pull the center of mass over in that direction a little bit. The way you would do the calculation is that the location of the center of mass is going to be the weighted average of the center of mass of the position of each of the things that are in the system. And what I mean by that is it'll be the mass of the first object times the location of the first object plus the mass of the second object times the location of the second object. And then if there's more than two objects, you'll just add more terms there. And then in the denominator, you'll take the total mass of all the objects added together. So in this case, for example, let's call this to be x equals 0 over here. It doesn't matter where you put x equals 0, as long as you make a choice and you stick with it. So if that's x equals 0, I'm going to have basically m1 is m, x1 is 0, because that's the first mass, and then the second mass is 2m, and it's at location x equal L. So as a result, this formula would give me 0 plus 2ml over m plus 2m. So that's going to be 2ml over 3m. So that'll be 2/3 of L. So in other words, it's going to break down as 1/3 L and 2/3 L for where the center of mass is located. So for this object, because the one mass is heavier, it'll shift it to the right so that it's 1/3 of way from the heavier mass. But anyways, the important thing is we have this concept of an object's center of mass, which is kind of our center point from the standpoint of applying Newton's laws. And it's, on a uniform object, it'll be in the middle. On a non-uniform object, it'll be more towards the heavier side of the object. We're not going to dwell on all the details of this, but that'll just give you a rough conceptual idea of what's going on when we start talking about objects rotating.